Well, it looks like it's the official time. Welcome back, everyone. Sorry about the snow, but we'll get through it. I did want to mention, since we're starting to get the inclement weather that Idaho always loves to lavish on us, don't forget that there's ways to always take a look at the recordings. If you miss a class, it's always going to be posted right away. And if you know that you might not be able to drive to class, but you would still like to participate, just send me an email about a half an hour before class at the latest, and I can send you the Zoom link to join class virtually if you'd like. That way, if the roads are terrible, don't risk your life over statistics. It's not worth it. There's always a way to get that information later on a bad day. Today wasn't too bad, but it's coming there. It's coming slowly. And for where we're at today, we're just going back to section 9.3. We're going to finish off the confidence interval that's left there and potentially start that one here, the additional exercise. If we don't get to it today, we'll get to it when we come back next Monday. And also our 10th quiz is posted. This one's pretty much just doing a confidence interval, very similar to how we're going to do them on our examples above. Well, any questions so far, folks, at the moment? Okay, I guess I do have a question for the class. This is kind of a poll, and we don't have to decide right away. But I've noticed on the schedule next week, on Tuesday, that's Halloween. And Halloween can be tough on a night class, especially if we have other children that we're possibly doing things with and things like that. I'd hate to interrupt Halloween. That'd be terrible. So I'm thinking about just canceling it. How do folks feel about that? Some are not too opposed. Okay, we'll probably make that official. I'll mention it again on Monday. Halloween will just be an off day for us. We're working pretty hard. We're caught up with the schedule, so that shouldn't cause any trouble. And will give us a chance to kind of take a breath after getting through confidence intervals right before going into hypothesis testing. Well, any other questions or comments, folks, before we take another look at these things? Okay, well, we left off on example, I believe it was 2. And this is what the Moodle website looks like before I had to unshare the screen and reshare it to make the recording work. It's a different way to present doing a confidence interval. The first thing you would have to do is specify a level of confidence. It becomes a central probability, so no percent symbol. This equation gives you the area in the left tail, from which you get negative z star. And everything starts falling into place in the formulas below. But one super important takeaway about this is, especially on exam 3 and the final exam, if you're doing this confidence interval procedure, p hat plus or minus z star and standard error p hat, you definitely want that table right there. It just spills the beans on the most common levels of confidence, so we don't have to constantly reinvent the wheel and produce 1.96 at 95% confidence. For these procedures, this is unchanged. So let's take a screenshot of that and take it along with us. Let's just place it maybe right over here. We'll probably need it at that point. Then after we collect our z star, we just go to the sample data. P hat is going to be number of successes, the thing the study is most primarily interested about, divide by the sample size. Now you have a proportion, or you could think of it as a percentage of the sample that qualifies as a success. We place it here and subtract our z star. And the standard error right here is calculated in that usual way right here. So that's the full walkthrough of our formulas. And honestly, it's terrible when you look at it from top to bottom. That's a lot of stuff. But we've been looking at each individual part, like the normal curve, standard error, and those kinds of things individually. And that's how it all comes together. So let's take a look at our problem down below and see how to get an interval out of this information. Any questions or comments first, folks, before we start this one? Okay, so this one is from 1974. That's some pretty old data, but it makes for a great statistics problem. It says here, to evaluate the policy of routine vaccination of infants for whooping cough, adverse reactions were monitored in 339 infants who received their first injection of the vaccine. That seems to be primarily about what we're interested in. It says next, reactions were noted in 20.35% of the infants. Let's give that a color blue to start us off. And if you want to read that study, you could go here, but it's never required. So that's all the information so far. We can start by writing down what we know. The sample size N is 339 infants. Or if you just said 339, that's totally fine as well. But they didn't give us the number of successes. They just said 20.35% of those infants had adverse reactions. So we're going to write down, this time it'll be p hat. We can't use 20.35 because p hat, much like a probability, is between 0 and 1. So decimal shift 2 places to the left to 0.2035. And that's the p hat, the sample proportion of successes in this problem. So like we mentioned before, sometimes they just tell you the number of successes. Other times they report the statistic. But what's tricky about this is when they said 20.35%, they were referring to the infants. We had to know it was the statistic p hat. Yeah, go ahead.
So p hat is the number of successes.
Mhm.
The problem is the number of failures. Is that the same thing?
It would be different, yeah. If they gave us the number of failures, then we can go 1 minus, say, q hat, for maybe that was the sample proportion of failures, and we would have gotten a p hat out of it that way. But I should say for a lot of these problems, it would be kind of untypical for them to mention the failures, because the study is only really going to want to talk about the thing that they're mainly interested in, which in this case would be the reactions that were noted in those infants. That's awful in a certain sense. A success just means we're interested in that in the study. And sometimes it's really morbid to say a success is an adverse reaction. We don't mean it was good, it was just means it's a thing we're interested in the problem.
So even though the reaction in time is being
Mhm.
20.35%.
It is, yeah. It's pretty terrible in a way. If we're studying like a horrible disease, we might say there's 32 successes, 32 people who have that disease. Awful thing to say, but we just mean that's what we're interested in the problem.
So I don't need to worry about one line.
I would say not. I would say no. It would be kind of unusual for the problem to focus on that, but really mean they're interested in that. Yep, you bet. Thanks for asking that question. Other questions so far, folks? Okay, so the setup is we have 339 infants. They're giving a whooping cough vaccination. I've never seen actual whooping cough in front of me. It sounds terrible. But they also looked for monitored adverse reactions and found 20.35% of them had those reactions. Now, to go through the method of doing the confidence interval, really the first thing we want to do is describe that unknown parameter. I'm going to use blue again because I'm talking about the thing p hat is estimating. But this is a value that, like we mentioned before, where we can't put a number on this one. This is the unknown. Yeah, go ahead.
So, sorry.
Oh, no
I was
worries.
trying to look at this earlier today.
Mhm.
Do you have the definition of unknown parameter?
Yes, the definition of the unknown parameter would be, let's put it down right here. The unknown parameter or unknown population characteristic is a value that describes the population. And there's really two kinds. We're going to see in this chapter 9, chapter 10, this kind of thing. P, the one that we're about to describe right above, is going to be the true proportion of successes in the population. So that's one symbol that we'll be using. And when we go to chapter 4, we're going to look at confidence intervals again, but we'll be dealing with quantitative data or numerical data is how we typically say that. And the unknown parameter or unknown population characteristic in that case would be mu, which would be the true mean or average of the population. It might be average, say, height, if that's what the study was about, or average GPA, anything like that, which would be numeric. So that's what we're thinking of when we say unknown parameter right up here.
But we're not using that.
Yeah, exactly. That's a good comment to make here, that this top one right here, let me get a good comment pen. This one is chapter 9, the one we're currently in, and in chapter 10. But we'll go to this one. This is pretty much the last part of the entire semester. We'll be doing this in like the last 2 to 3 weeks, probably about 2.5 weeks. This one will be in chapter 12. It's kind of strange, but the mean is actually a little bit tricky. So we're saving that one for last. Other questions so far? Thanks for asking those questions. And really, this is the hardest portion right here of the whole conference interval procedure. So it's very worthy of our time to be careful with this, be really clear of what we mean. And I went with parameter once again. I'm going to try to get into the habit of writing this in as population characteristic, like our author does. I'm going to double check my notes and make sure those don't keep on sneaking in. Let's put that in red, just for that quick edit. And now, well, the trick for trying to get this value is, recall p hat estimates p. That's the statistic, which is trying to approximate the unknown population characteristic. And so if we think of what this is saying and just say it in words, we can fine tune it and redevelop a new sentence for the population characteristic. So let's go over here. P hat is a statistic, so we'll say sample proportion of successes, reactions to the vaccination was 0.2035. So over here, we're going to say this is the true proportion of all adverse reactions to the vaccine for all infants giving their first injection. It's a lot of words, but let's put this down. P equals the true proportion of all infants that were really interested in the adverse reactions. Those are the successes that have adverse reactions to, and what you could say here is the first injection of the whooping cough vaccination, or if you decide to paraphrase it, you could just say adverse reaction to the vaccination. That seems kind of alarming, but in these kinds of problems, if you say vaccination, you are essentially meaning whooping cough right away. So you don't have to bring everything into the context. If you paraphrase a little bit, a reasonable amount, that is okay for full credit as well. Well, any questions, folks, with that statement? Yeah.
So when you're asking for the unknown parameter, like quiz and whatever, is it always going to be a sentence? It's not going to be an actual number.
Exactly, yes. And that's the thing that makes it really confusing. It's so tempting to put in that value when we're trying to discard what P is, but it can't possibly go there. That's the unknown. So that's absolutely correct. And that's worthy of a comment as well. Let's put it right here. For this question, we are describing P, but we cannot, let's see, what's a good way to say this? Use a number. Let's say it that way. Use a number because the true value of P is unknown. All we have is that as an estimate. All the questions so far about that first part A? Okay, thanks for the questions on that. And like we mentioned, it's not going to get the most points on a full problem like this one, but it's the trickiest part. And if we can't get this right, it means this portion, the practical interpretation, suddenly becomes just a huge box of mysteries. That's really hard to unpack. unless we actually know what the parameter P is. Well, now that we have that, we'll check conditions. And the conditions checking, well, there's two stages. We first see if there's any information about randomization. Doesn't look like there is. And if you skipped that, I would be okay with that. I would typically want to say something personally. So I'd probably say in this problem, well, it's not known if these were really randomly selected 339 infants, but they probably were. This is a premier journal. They are not going to publish something if it wasn't a random sample. But just as a reminder, we're pretty much just going off the information that was given right here. You don't have to look up the study. That could be costly and tedious to do. So by the information given, I'll just say it is not known if the 339 infants came from a random sample. But regardless, we can still check one feature of the study. The sample size of 339 had to be high enough so that the central limit theorem can be used. And so we can calculate things like standard error, critical number Z star, and get really meaningful computations out of them. So here's how that check will go. This time we're going to actually use the equation n times p hat because that's what they supplied us. They didn't say the number of successes or failures. So here's the next thing we'll try. N times p hat. Let me try this a slightly different. Let me start with a sentence that just says number of successes in the sample. You don't necessarily have to write that, but it's just to be clear, that's what we're calculating when we put down the formula, n times p hat. So this quantity, whatever it comes out to, it has to be larger than 10. Looks like we should be in great shape. That's a pretty large sample size, but we still have to show the number here and go through the motions. Let's grab our calculator. Probably make that a little bit smaller. See if we can make this work side by side. It's kind of tricky. So first, n times p hat is going to be, oh geez, I guess this should go down below. Sorry, just trying to rearrange our windows. Maybe we'll go full screen. We'll just try to do it the normal way. So we'll put in our sample size at 339. Multiply it by the value of p hat, given right up here at the top, 0.2035. And here's the value we're going to get for the number of successes in the sample. Now keep in mind, when they gave us p hat, they probably rounded, which means we might not get a whole number. That's not to be a concern. We'll just round to the nearest whole number. So over here, it's 339 times 0.2035. And our result is, I would round this to 69 observations altogether. So 69 infants had adverse reactions. That's greater than or equal to 10, so we're in great shape. I'll put a check mark right there. Then we do it again, number of failures in the sample. This one is going to be equal to, they give us a formula, but in all honesty, we really don't need the formula. I'll put it down here in case folks do want to use it. It's going to be n times 1 minus p hat So what you would be putting in the calculator if you decide to use this formula is 339 for the sample size n, 1 minus 0.2035. But here's how I'd probably rather calculate it. I'd rather just go to the sample size of 339, subtract from that the number of successes at 69. And that's probably what I would do, just put down a 270. But if you did go this route, there's no harm in doing that. It's a bona fide formula. You could take 339 1 minus 0.2035. And we'd get a value which we'd round to 270 anyways. So same conclusion either way. I think doing the 339, the total, minus your number of successes, probably the easiest way to go through. There'd be less chances of me making a silly mistake in the calculator. So 270 definitely meets our benchmark of greater than or equal to 10. And so we can say here as a conclusion, the sample size is large enough. My penmanship seems to be degrading as the week goes on. Enough. There we go. So we're done with the condition checking portion of the problem. I won't ask for conditions on every single problem we do. It could happen on a quiz, but if it's taken off, then it's considered optional. On exam, I might even take that off just to make the exam more reasonable for 50 minutes. Major reason we're doing the condition checking is, well, it is important. And also it's a WebAssign problem on virtually every problem I think on there. So it's good to take a look at. Well, let's now go to the big thing on part C. We want a 99% confidence interval. And the way this problem is written is kind of tough. It just says, produce the confidence interval. What is going on in the quiz is a little bit different. Let's take a look at it just to peek at how this one will go. Quiz number 10 is more similar to example number 1 in those notes, where instead of just saying construct a confidence interval from scratch, it breaks it down into parts. You first want to calculate the sample proportion of successes, then calculate the standard error, and then bring all that together in part D. I think this is an easier problem because of the way it's broken up. So that makes part C kind of challenging. It just says do it in one shot. Sometimes that's what WebAssign does, so we're going to try it this way for practice. Any questions or comments first, folks, before we begin? Yeah.
So the 10 is like a set number that we're always going to use. Like kind of meets the condition, right?
Exactly, yes. And if you're curious where it came from was directly from the central limit theorem. Our sample sizes had to be large enough, so number of successes, number of failures, both exceed 10. So that condition is only there so that the central limit theorem actually works and our confidence interval is accurate. Other questions so far? Okay, so back down to this thing. Let's get some extra space in, just for good measure. First thing I would do in doing this problem is you pretty much definitely want to write down the formula first. It'll go p hat plus or minus a critical number z star multiplying the standard error of p hat. Oh, I still need green. Let me fix that. Okay, so we have our formula down. And the reason this is so vital is we're pulling in information from a whole bunch of different variables and sources. If we don't write down the formula first, I don't necessarily know what's going on paper. So this is like the guide. Next thing we start doing is look up values. Problem directly gave us p hat, so we'll plug that in later. Z star, that one's actually supplied because if they say 99% confidence, we go to this row. Our Z star is going to be the 2.58. So that one's down. So P star is ready to go. Or excuse me, P hat is ready to go. Z star is just fine. What we need to calculate next is the standard error. That's the one that's sometimes the most trickiest. And if I was going to make a mistake on part C, it's probably right there is where that mistake is going to happen. So let's do this one really methodically, really carefully. We need to reveal P hat, but let's just copy it down. That might be easier. That's not a good place to put it. Let me try again. Okay, so that's the next statistic. And we'll write out here first, standard error of P hat by formula is the square root of we take the statistic p hat, multiply by 1 minus p hat, and divide that whole result by sample size n. So now, again, just like the confidence interval formula, the best way to be really accurate is write down the formula first. Now that the standard error formula is written down, we can just look up values and carefully plug them in exactly where they should go. So next, this is equal to square root of, in place of this p hat where the red dot is, 0.2035. Then it's a 1 minus 0.2035 again in that location. Now we take a division by the sample size n. And again, this is a good reason why it's a good idea to put in the margin somewhere these values as soon as you spot them, because it will remind us, our brain is just ready for it. The moment you see n, think 339. So down below, 339 for the sample size. And now let's get this all calculated out. So in the calculator, let's make this bigger so we can get this in really precisely. First thing you need is a square root symbol. So I'll go second power 2 to call it up. Then inside the square root, put in 0.2035 times 1 minus 0.20. Oh, let me try again, 2035. Close the parenthesis, hit division, and 339. Now, when we hit enter on this, we actually need to be a little bit careful with these instructions right here. It's asking us to round to 3 decimal places, but the thing that we're rounding to 3 decimal places is the confidence interval. If I round this to 3 places, I might not have an accurate enough answer when we go to our end solution. This could potentially become a problem with WebAssign. So the good idea for these instructions, carry 1 extra decimal place of precision and only round your final answer to the 3 decimal places. So this is 0.0218. I'm going to round it to 0.0219 for 4 places. We'll use the 2.58. This is what WebAssign is expecting for their value there. And for p hat, we have, oh, it's down below, to 4 decimal places, that value here. So now we're ready to just drop in each one of these values that we found. Any questions so far, folks, before we go to the next computation? Okay, so back over to the confidence interval. That's right here by the red dot. Plug in p hat. Down below, it's 0.2035. We have to use this formula twice, with a plus and then again with a minus. I said that in a weird way. Usually we do the minus first. Then next, Z star. This one's a table lookup because it's a typical confidence at 99%. So 2.58. Then last thing to look up is standard error p hat. That's right over here, the value we just calculated, 0.0219. So that's a confidence interval so far. And now we're about ready for the final steps on this. What I would do next is, let's go back to this P right here. The confidence interval is estimating this thing. So one way to present your answers, which does help with the interpretation, is to take this P, come down below, and we are estimating it with an upper bound that goes to the right and a lower bound that goes to the left. To get the lower bound, we'll use the minus sign here. And so now it's pretty much just calculator work from here on out. Let's type this all in, first using a minus sign. So it's 0.2035 minus 2.58 times 0.0219. Double check that is always a good idea for these kinds of things. 0.2035 minus 2.58. I use a time symbol this time. Usually I use parentheses, but for one reason or another, I use that symbol. 0.0219, I think it's all set. So that should be our lower bound. And this time we're rounding to 3 decimal places because we're getting our final answer now. 0.147 for the lower bound. Then the next thing that I do in the calculator is really because I make mistakes when I type all this in. It's easy for me to flip a digit or mess with a decimal. Up arrow twice, highlight the thing you just calculated, hit enter, and switch that sign to plus. Now we're doing upper bound. And this one comes out at 2.60. I said that in a weird way. I need to really watch my decimals. 0.260 is what we get on this one. And I'll put a box around this because we have work sort of everywhere, but that's our confidence interval finally. The true proportion P of something is between 14.7%, if we think of it as a percentage, and 26.0%. So we did it, folks. That's the full confidence interval. All that's left is interpretation. And really the interpretations aren't so bad because we've been trying to do that all along with all of our probability computations. Any questions at all, folks, on getting that confidence interval here? Okay, one thing I should mention is there is a couple ways to write this interval. This is a so-called inequality form because I'm using a less than sign twice and placing P in the middle. But another way you could write this interval, which is equally valid, would be like this. .147.260 is another way to write the interval. If you're writing it this way, then you're using in mathematics interval notation. The parenthesis here is saying we're going from 1.47 up to 2.60, excluding those values. That's why we use a less than here, a less than here. We're excluding the 1.47 and saying we're larger than that value. So if you write it out this way, that's completely fine as well. And when you go to put your answers into WebAssign, it pretty much looks like this. They give you one box, another box for two of your numbers. They're thinking of this format when they do that. We always have to give the smaller number first. So lower bound always comes first, no matter how we write it, and then the upper bound. Well, next thing we need to do is interpret our answer. To do that, we need to go back to what we said all the way up at the top right here. The thing we're estimating is P. We now know that P is between those two ranges. And so this is what I would do for a practical interpretation on this problem. We can now say, with 99% confidence, that's the level of confidence we used. So with 99% confidence, now that we've said the confidence level, we go back to P. We just have to say what it is. So we'll read out this statement. The true proportion of all infants that will have an adverse reaction. Again, you could say to the whooping cough vaccine. If you paraphrase to just the vaccine, that's completely fine as well. I'll paraphrase this one to the vaccine. So we said what P was, we mentioned this. Now we're just going to say is between .147 and 0.260. So that would be my statement here. Honestly, I'm not completely happy with it, but I left it as proportions just to say that's a completely fine way to go as well. Another option you could put in here is if instead of saying proportion, you said percent, then just come down over here. You're saying 14.7% to 26.0%. Either answer is totally acceptable. But I usually think of these interpretations as percentages just because they're more easily understood when you're explaining your confidence interval. Then we did it, folks. That's our second run through of the full confidence interval procedure. Any questions or comments at all in getting that conclusion? Okay, and we might wonder, why would a government agency even do this? Well, back in the, what was this, late 70s, or this was mid 70s, I'm not too clear on the history of this vaccination, but they might have had some concern of just how dangerous this vaccination was when it was first initially released. And so when they ran the study, they probably also had some kind of benchmark. They might have decided, well, if the reactions we're looking at are serious enough, and if it's plausible that the percentage is maybe larger than something like 30%, that might have been a problem in the vaccine. They might have slowed down trials and tried to work out how to reduce those reactions. So having an estimate of what could happen is now suddenly incredibly valuable in these kinds of contexts. We're looking towards possibilities in the future and trying to watch out for warnings that could come up with any kind of process we're dealing with, like vaccinations. Now, down below, we have the concept questions, but before that, any questions at the moment? Okay, the concept questions here, I feel like they're a little bit overdone for an introductory class on statistics. They're pretty tough questions, and the only reason they're here is some of the questions in WebAssign have parts attached to it, which I cannot remove, which are concept questions. So I'm going to think of this as really a guide for WebAssign primarily. I'm not going to re-ask these questions for credit on quizzes or exams, but when you go into WebAssign, you're asked a weird question like, if the confidence decreases to 90%, is the interval wider or narrower? Come here, that's where we're going to address all those questions, really just to help out with WebAssign. And it's important too, so it's kind of more than we needed. But it'll help for WebAssign. So for the concept questions, we're wondering what's going to happen with the confidence interval. Will it become wider and narrower with each one of these questions? And here's the reason why we care. A wide confidence interval is useless in a certain sense. If this was, say, between 2% and 98%, that's a huge range where the true proportion could live. We want our intervals as narrow as possible so that the statement we make is precise as possible. If we said that it was between maybe 14.7%, or excuse me, 14.7% yes, and maybe 16.9%, that's fantastic. Not because this number is low, it's because there's not too much range between those two numbers. It means there was very, very little error in estimating. So now we're wondering, in what ways could we make the interval become narrower? And that's the good situation. Let's put here just as a quick note. Narrow intervals are better because they give us more precise estimates. Let me try to fit that in. I didn't think of how long that sentence was going to get. Because they give more precise estimates. So think of narrow as being the good thing. A widened confidence interval is more and more useless the wider and wider it becomes. So here's our first statement. It says, if the sample size were to increase, would the confidence interval become wider or narrower? And we'll explain it as we go. Any volunteers for your intuition on this? Is this a wider interval or a narrower interval for a larger sample size? It's kind of a tough question in a way, right? Yeah, go ahead.
Narrower.
Absolutely. If we increase the sample size, that's always a good thing. We should be getting more precision with a higher sample size. And so we're getting the thing we want. We're narrowing our confidence interval by pulling in more and more data. But let's see if we can explain it. That's the challenge on this. We'll say narrower because the interval has the form p hat plus or minus z star times this thing. Let's use a different color maybe. This one was green, times standard error of p hat. And the thing that's special about that is standard error p hat. We looked in section 8.2, the larger the sample size, the smaller this becomes. It's square root of p hat, 1 minus p hat, divide by n the sample size. Now we can say the larger n, we found in section 8.2, larger the value of n, the smaller the value of standard error, the smaller standard error p hat becomes, and only because if you multiply by a number that's getting smaller and smaller, this is causing the interval to become narrower right in that location. So the smaller the standard error p hat becomes, which narrows. Oh, I did something to my pen. Let me fix this. Okay, it's back. So I ran out of ink. It narrows. Does that make sense to folks on this assessment right here? Okay, so the good news is, if you do the thing that you expect is a good thing, increase the sample size, you're rewarded with a better confidence interval. It'll become narrower. It'll be a more precise estimate altogether. Well, let's try this again. Next question is about changing the confidence. We did a 99% confidence interval, and now it's asking if the confidence level were to decrease to 95%, we want to know where we get a wider interval or a narrower interval. This one's kind of tricky, but any volunteers for a reaction on this one? Yeah, go ahead. So we're going to decrease to 95%. I actually have to think about that one. Would it become wider or narrower? I think this one actually goes the opposite way, which is really, really weird. But let's take a look and see if we can express why it should go one way or another and see what happens. So our confidence interval is p hat plus or minus a z star. This time I'm highlighting the z star with a special color because if you change the confidence level, that's the only thing that updates your critical number z star. Everything else will stay exactly the same. So let's keep it in black to not focus on it as much. And now we can say at 99% confidence, I'll use conf for confidence just as a shorthand. Z star was, I think it's a 2.58, but let me double check. We just did 99% confidence. Yes, 2.58. Definitely not a number I've memorized. And at, it says decrease to 95%. So let's say at 95% confidence, Z star decreases to 1.96. So I believe you're absolutely right. If we decrease our confidence, Z star goes down, and that's going to make our interval narrower. This is actually really dangerous, but let's put our conclusion here. Therefore, the interval narrows. Now let's pause here for a minute. This is really, really weird in statistics because decreasing your confidence, that's not good, right? You're less confident. You have a less % chance that our method will truly capture the unknown parameter P. But if you decrease your confidence, in some weird roundabout way, we're rewarded with an interval that looks more precise. This is the major reason why we have to always state our level of confidence right here every time we interpret an interval. Because we could convey that our interval is super precise by doing like 3% confidence. And again, that's one thing that's really nasty about these kinds of intervals. If you are more confident, that means it's more likely you've captured the unknown parameter with your lower bound and your upper bound. That means your interval has to widen to get that increased chance of getting the true population proportion. So that one's really very weird. Good intuition on that one. Now let's try one last one. Any questions at all, folks, so far? Okay, to me, this one's kind of the weirdest one at all, part G. It's weird like part F is, where things are just run counter to what we'd like. Decreasing the confidence, which is bad, rewarded us with a narrower interval, which looks good until you state the confidence. Here's something else is happening. It says, assume the sample size won't change. Confidence interval, confidence level won't change. And suppose the sample proportion of successes, it was 0.2035, but let's pretend just for the moment, it was different, that it was 0.30. Maybe there was a problem with the study and they corrected all the results and they found out, oh, it was a lot higher than they thought. So we're changing this value. The question becomes, would the resulting confidence interval become wider or narrower? And again, these are pretty tricky questions. Any volunteers for this one? Would you say wider or narrower in this case? Honestly, for me, this one is kind of a pot shot almost, right? I believe that this one, it widens, but we need to explain that. There's no great explanation until we put down something on paper. So I'm going to put down here, if P gets closer to 0.5, the interval becomes wider. That deserves an exclamation mark. And let's explain why exactly that would happen. It turns out it's about the standard error on this thing. So let me write down the formula again. P hat plus or minus Z star times the standard error of P hat has this formula. Standard error of P hat is the square root of, let's do a different color here to make this show up. P hat times 1 minus P hat. Oh, we should probably use blue. That makes a little bit more sense. P hat times 1 minus P hat divide by 339. That portion's not changing. So this is what our standard error would look like. And let's look at P hat times 1 minus P hat. If we take a 0.2035, times 1 minus 0.2035, we get this number, 0.1621 if we round. But if we do it with a 0.3, it increases. This is kind of strange. 0.3 times 1 minus 0.3 is bigger, 0.21. And it's only because we got closer to 0.5 when we changed the statistic. So it becomes wider in that sense. Here's what the picture really is on this. We're taking a P, I'll just leave it as a P since I can't put in P hat, times 1 minus P. The valid values for P is between 0 and 1. And so this is the graph of P hat times 1 minus P hat. Its values get larger and larger and peak right here, exactly at, if I can nail that, 0.5. That's the largest this numerator inside the square root ever becomes. And it's just a weird consequence of the algebra of that statement there. It'll widen the interval the closer you are to 0.5. That's not something we can control, but it's something we should be aware of. If we suspect our statistic takes a value close to 0.5, then we're just gonna have a wide interval because math is the way it is. It's gonna punish us. We're probably gonna need a larger sample size to compensate. If we suspect it's gonna be close to 0.5. Well, that looks like all we have time for today. Here's the 0.5 that was being mentioned and that maximum value. But any questions, folks, before we call it a night? Okay, well, have a wonderful night, everyone. When we come back next class, we'll take on that additional problem. Then we'll move over to chapter 10 after that, forgetting where we're at.